So last class we have been discussing about gas chromatograph various components. We have seen about the carrier gases that have been used and what are the associated attachments to it. That means the pressure regulators, the flow meters, etc. And the purpose for that. We have also seen the sample injection port where we have discussed about how the sample is introduced into the column. Uh, it is first actually introduced into a port that is heated in order to cause instant vaporization of the sample and conversion into the gaseous form. The gaseous sample then enters the column. Then we saw about the column, the different types of columns. We have basically two types, that's packed columns and capillary columns or open tubular columns. We have seen packed columns are the ones that are used in GLC and it can also be used in GLC. But GLC nowadays sees more usage of the open tubular columns. Open tubular columns again were of different types. Fused silica, open tubular columns, wall coated open tubular columns, support coated open tubular columns. These were different types of columns under the capillary columns. And lastly, we saw this slide last time, that is a comparison between the packed columns and the capillary columns. So from this comparison, you could easily make out that capillary columns give you much better separation. As you can see here, you get much sharper peaks, and also the number of theoretical plates is much greater in case of capillary columns. You have about 5 lakh theoretical plates in a given column of this length and diameter. This, in case of packed columns, it's very much lesser. So it's only about 10% of this. So there, if you have more theoretical plates, then you get better separation. Now, also you have seen the length, mainly the length and the diameter. There's a lot of difference between the two. The length is very long, and as I have been repeatedly telling, in any chromatography, if the length of migration of the mobile phase and the sample over the stationary phase is increased, then you get better separation. You can see the very long length compared to the packed column. Definitely that will give you much better separation. You can have this very long columns without affecting the flow rate because of the very unique feature of capillary columns, and that is there is no obstruction to the flow of the mobile phase in capillary columns because the stationary phase is always lying on the inner wall of the capillary column. It does not fill into the column, and that's why there is absolutely no hindrance to the flow of mobile phase. So this is where we stopped last class. We'll continue from here. I've also been telling that the column must be kept in an oven. So we'll see something about the oven. What are the features? What are the adjustments, parameters we should consider? Column temperature is an important variable that must be controlled to a few tenths of a degree for precise work. This means that even a small variation of 0.1 degree would also affect your separation. This is because that could affect the sample or one component in the sample, whether it is present in gaseous phase or not. And that will affect your ultimate separation. Thus, the column is ordinarily housed in a thermostated oven where the temperature is very precisely controlled. The optimal column temperature depends upon the boiling point of the sample and the degree of separation required. So if the boiling point of the sample of the least volatile component, which has the highest boiling point in your sample, if the boiling point is very high, then you will have to keep the column also at a temperature much higher than the boiling point. How high? Roughly a temperature equal to or slightly above the average boiling point of a sample results in a reasonable elution time, 2 to 30 minutes. 30 minutes is quite a long time, but if you have a lot of samples, then it will take you a longer time. For samples with a broad boiling range, it is often desirable to employ temperature programming, whereby the column temperature is increased either continuously or in steps as the separation proceeds. I told you about temperature program GC when we saw about the modification. So if your unknown sample has a large number of components and the components have varying boiling points, then you will have a broad boiling point range. And in this case, it is always better to start at a low temperature suitable for the most volatile component, that is, its boiling point can be exceeded, and then slowly at regular intervals, the temperature is increased until the least volatile component is also eluted. That is, its boiling point is also exceeded and it also gets eluted. This is what was temperature programming. So this also can be done for the oven. You can be varying the temperature of the oven where the column is housed. Next is the solid support material that we use. Now, what is this? This could be the absorbent itself, or it could be, it could be the stationary phase, or it could be a support material. Now, I'm talking about actually the support material only. So, this is with reference to DLC. DLC where you have a liquid stationary phase. The liquid stationary phase must be coated on a solid support. And that's what we are going to discuss now. The most widely used support material is prepared from naturally occurring diatomaceous earth, which is made up of the skeletons of thousands of species of single-celled plants, that is, which are called diatoms, and hence the name diatomaceous earth. These cell plants that inhabited ancient lakes and seas. Such plants received their nutrients and disposed of their waste via molecular diffusion through their pores. As a consequence, their remains are well suited as support materials because gas chromatography is also based upon the same kind of molecular diffusion. And that's why generally we have this type of support material being used in teaching. What should be the particle size of the support? The efficiency of a gas chromatographic column increases rapidly with decreasing particle size of packing. Clearly indicates as you decrease the particle size of the packing, what will increase? The surface area. The surface area of the support. If the surface area available in the support increases, then more amounts of liquid stationary phase can be coated on a given amount of support. If more amount of stationary phase can be coated, then naturally more samples can be separated. The pressure difference required to maintain a given flow rate of carrier gas, however, varies inversely as the square of the particle diameter. So now we see about the mobile phase. DC separates solutes based on their different interactions between mobile phase and stationary phases. The solute's retention is determined mostly by vapor pressure and volatility. So this, it should be volatile, so its retention is dependent upon its volatility. Solute retention is controlled by its interaction with the stationary phase. These are things that you already know. Now, the carrier gas, which is the mobile phase, main purpose of the carrier gas in GC is to move the solutes along the column. Mobile phase is often referred to as carrier gas. It must be inert. These are things we have already seen under carrier gases. Common carrier gases include helium, argon, hydrogen, nitrogen. Carrier gas or mobile phase does not affect solute retention, but does affect. See, we keep telling that the carrier gas has no function other than to carry the sample component, but it has an indirect effect on the separation. What are the things that it affects, which will indirectly cause some changes in the separation of a sample? It will affect the desired efficiency for the GC system because low molecular weight gases like hydrogen and helium, they allow larger diffusion coefficients and they are also faster, they give much faster and more efficient separation. Because they can travel much faster, they will give you faster separations and more efficient separations. No band broadening takes place. This is one effect that you see based on the mobile phase, where if it is low molecular weight or light gases like hydrogen and helium. Secondly, the mobile phase can also affect stability of columns in situ. Suppose the mobile phase is hydrogen or oxygen, it can react with functional groups and solutes and stationary phase or with surfaces of the injector, connections, and detector. Any of these types of interactions will definitely affect the separation of your unknown sample. Response of the detector can also be affected by carrier gas. Thermal conductivity detector requires hydrogen or helium. That means what it actually requires is a carrier gas with a high thermal conductivity. Then the sensitivity of the detector will be very high. This is one of the detectors which will be studied. Other detectors require specific carrier gas based on their compatibility. We will see this when we discuss about detectors. These are the detectors which is the most suitable carrier gas. So these are the effects that are produced which indirectly actually affect your separation. So though we say carrier gas does not affect solute retention, it does not affect it directly, but indirectly it could have an effect. The stationary phases, we come to stationary phases in GC, main factor determining the selectivity and retention of solute. Because the effect of mobile phase is not a direct one, it is the stationary phase that is mainly responsible for retention of solute. There are three types of stationary phases used in GC: solid adsorbent, or it could be liquid coated on solid supports, or it could be bonded phase support. So these are the three which we'll go through one by one. In gas solid chromatography, you will be using solid adsorbent. So the same material is used as both stationary phase and support material. Because there's no support material like that, the stationary phase itself is the support material. Common adsorbents include alumina, silica, you're very familiar with this. Apart from that, molecular sieves, which could be natural clay or it could be crystalline aluminosilicates or also called zeolite. You can also have active carbon. Now you can see this is a picture of active carbon where you see the magnified pores in the activated carbon. These are the other zeolites that the advantages of gas solid chromatography, it has long column lives and it does not deteriorate so easily. So it has a long column life and it has an ability to retain and separate compounds not easily resolved by other GC methods. That could be GLC or any of the others. So with that, which are those type of compounds? Geometrical isomers and permanent gases. Because especially the geometrical isomers, these are separated only by gas solid chromatography. Because these are isomers with spatial arrangement differences. Now, since gas solid chromatography deals with separations based on absorption and differences in absorption coefficients, which are directly related to surface phenomena, how it gets attached. So any changes in in a molecule, spatial arrangement of the atoms in a molecule, that will show a difference in the absorption towards an adsorbent. But the same two isomers may have very similar solubility in a liquid, and therefore it's not easy to separate them by gas liquid chromatography. It is possible to separate them by gas solid chromatography, but not by gas liquid chromatography. So that's a major advantage of gas solid chromatography. The disadvantage is very strong retention of less volatile or polar solutes. The polar solutes are very strongly retained and it's very difficult to elute them, so they will take a long time to elute and your analysis will also take a very long time. The less volatile components will also get absorbed on the stationary phase, and since they are not so volatile, they will not go into the gaseous mobile phase. So these type of compounds are very difficult to elute. The catalytic changes that can occur on GSC support. This is also possible because adsorbents may undergo certain changes because of catalytic reactions. And GSC supports have a range of chemical and physical environments. They have different strength retention types. They give non-symmetrical peaks, and they also exhibit variable retention times. Now, what does this mean? In a support in an adsorbed bin, a sample could be adsorbed at various retention sites, and each of these retention sites, that is, on the adsorbent where the sample gets attached. Now, each of these retention sites on the adsorbent could have different affinity towards the sample. So, a particular site is exposed, it will show a particular affinity, and another site is exposed, it will show a different affinity. This could cause distortions in the chromatograph ultimately. Non-symmetrical peaks are more common because you could get, these are referred to actually tailing in the peaks or fronting in the peaks, which are very common occurrences in gas chromatography. I will be telling you about that towards the end of this chapter. Where you do not get a symmetrical Gaussian shape. You get either the left side part of the graph extended or the right side part extended. If the right side is extended, we call it tailing, and if the left is extended, we call it fronting. Variable retention times may also be exhibited by GSC support. This is mainly because GSC uh, requires the stationary phase to be packed into the column. And if there is any irregularity in the packing or the packing is not very uniform, it could be non-uniform shapes and sizes of the packing material, anything. All these non-uniformities in packing will contribute towards edge diffusion problem, and that in turn gives you variable retention time. So it would be very difficult to identify samples if the retention time keeps varying. So these are some disadvantages encountered in gas solid chromatography, which uses solid adsorbents as stationary phase. Next, we have the gas liquid chromatography. And here the principle, of course, is light dissolves light because you have a liquid. If you have a polar liquid, then a polar component will easily dissolve. Now, stationary phase is a liquid that is coated on a solid. Suppose in this type of chromatography, you have over 400 liquid stationary phases available for GLC. The materials range from polymers like polysiloxanes, polyesters, polyethylene glycols to fluorocarbons and liquid crystals, etc. Based on polarity, out of the 400 phases available, only 6 to 12 are needed for most substances. This is what we see in gas liquid chromatography. So preparing a stationary phase for GLC. How is the stationary phase prepared? So slurry of the desired liquid phase and solvent, this is a volatile solvent, is made with a solid surface. So what is solid support? It's a substance which has absorbing capability. So to that, you will be adding the liquid stationary phase, which is mixed with 3 times its volume of volatile solvent. So all the three are mixed and a slurry is produced. Solid support is usually diatomic ethers, which are fossil cells of ancient aquatic algae or diatoms, or it could be the solid support could be a silica-based material. Once the slurry is done, the solvent is evaporated off, coating the liquid stationary phase on the support. The resulting material is then packed into the column. This gives you a packed column in the GLC mode. What are the disadvantages of gas liquid chromatography or done in a packed column? Liquid may slowly bleed off with time. This bleeding of stationary phase is a common occurrence in case of uh, liquid stationary phases whenever they are coated or absorbed onto solid support. See, in this case here you can see this pink uh, portion is the liquid stationary phase, which is held on the surface of this solid support. This is just a physical bonding. Now, because we are using gas, now this yellow portion could be considered the mobile phase. It's the gas in case of gas liquid chromatography. Because of the continuous flow of gas, what could happen is this liquid stationary phase, these are molecular layers, so this could be washed off into the mobile phase, physically washed off. And that is what is called bleeding of the column. Bleeding of the column means you are washing out the coating of liquid stationary phase. If this happens, then at a particular point, there is no liquid stationary phase. So there is no question of retention of the sample at that phase. So this will again lead to distortion of the chromatograph. This bleeding usually may take place, especially if high temperatures are used, that is, evaporation of the liquid stationary phase could take place. And if this happens, then it can contribute to background. That is, when you see a chromatogram, the liquid stationary phase may give a response, and you may get small peaks in the background or in the baseline. If this happens, bleeding, then it may change the characteristics of the column with time. That's what I first told you, that after some time you will see there is no stationary phase at certain points of the column. So even if the solute was supposed to get retained, it will not be retained at that point. So the separation effects are also changed because of change in characteristics of the column. And as time goes on, the more and more the column is used, more and more changes will take place. And that's the reason why you need to keep checking whether your column is still in the original shape or not. That's done by calculating the capacity factor. We'll see it a little later. Okay, next comes the third type, that is the bonded phase supports or cross-linked phases. This gives rise to the bonded phase gas chromatography. Here you have what you see is covalently attached stationary phase to the to the solid support material. So here also the stationary phase is coated on a solid support material, but in the earlier case we saw it was a physical adherence on the surface. But here there is a chemical or a covalent attachment or a bond formation between the stationary phase and the support material. Because of this bond formation, the covalent bond formation between the two, it is very difficult to detach the stationary phase from the solid support material. To detach it, you will have to break the bond, the covalent bond, and that requires much higher energy. So it's not so easily done. This will prevent, of course, column bleeding in here. Bonded phases are prepared by reacting the desired phase with a silica surface. So reactions form an SiO-Si bond between the stationary phase and support, reactions form an Si bond between the stationary phase and support. Any of these could happen. So you could have this or this. Many bonded phases exist, but most separations can be formed with the following phases, like dimethyl polysiloxane. This is it, the structure. Methyl phenyl polysiloxane. This is it. Polyethylene glycol carbovax 20M. This is the structure. The advantage of these bonded phases are they are more stable than coated liquid phases. I have been telling you that, so I'll not repeat it here because these can lead to bleeding. These are not. Like, they can be placed on support with thinner and more uniform thickness than liquid phases. This is true because there is a covalent bonding between the support and the stationary phase. So it is, say, one molecule can bond, then it will always be one molecule. So you get uniform thickness. If two molecules can bond, then it will always be two. So it will be, generally, it's more like one molecule, and that's why you get monomolecular thickness. So the thinner the stationary phase, faster the equilibrium that is achieved in a separation. That is when the samples come, they are distributed, and the distribution equilibrium is attained very fast. And so you can have faster flow rates, which is the case in gas chromatography, since the mobile phase is a gas. The stationary phase, so this is to summarize desirable properties for the immobilized liquid phase in gas liquid chromatographic column include low volatility. You have a liquid which should remain as a liquid throughout your experiment. So it should have low volatility. Ideally, the boiling point of the liquid should be at 100 degrees centigrade higher than the maximum operating temperature for the column. If a column is going to be operated at 200 degrees centigrade, ideally the liquid stationary phase should have a boiling point of 300 degrees centigrade. This is not a hard and fast rule, it's an ideal situation. But the boiling point of the liquid must be higher than the operating temperature of the column. Secondly, the stationary phase must have thermal stability. Because we are using high temperatures, it should not undergo any degradation, deterioration at very high temperatures. Thirdly, the chemical inertness is also a desirable property because the liquid stationary phase must not chemically react with the samples that are going to come into contact with it. And the solvent characteristics such that it should have solvent characteristics such that the K dash and alpha values for the solute to be resolved fall within a suitable range. K dash and alpha refer to the capacity factor and the separation factors. These are some parameters which are used to evaluate the efficiency of separation, which we will also be seeing after instrumentation. So by changing the liquid stationary phase, you will be able to change the capacity factor and the alpha value. So you should get desirable K dash and alpha values when you're using a particular stationary phase. So these are the desirable properties, four desirable properties of a liquid stationary phase. The retention time for a solute on a column depends upon its distribution constant, which in turn is related to the chemical nature of stationary phase. This is here with one example. I just clarify. Suppose say the stationary phase is polar and you have a polar solute. So it will be retained very strongly in the stationary phase because it is polar, and therefore its retention time will be much longer because it will not easily move into the mobile phase. It will be very strongly retained in the stationary phase, and hence you will get longer retention time. That's what is meant here. The retention time for a solute depends upon its distribution constant, which in turn is related to chemical nature of stationary phase. To have a reasonable residence time in the column, a species must show some degree of compatibility Here it refers to solubility with the stationary phase because we are dealing with a liquid stationary phase. That's why it refers to solubility. Here, the principle of light dissolves light applies, where light refers to the polarities of the solute and the immobilized liquid. Like I told you, polar solute retains strongly on a polar liquid phase. Polar stationary phases contain functional groups such as CN, CO, OH, hydrocarbon type stationary phase, and dialkyl alkyl siloxanes are non-polar. So these are the polar ones, these are the non-polar ones, whereas polyester phases are highly polar. Polar solutes include alcohols, acids, and amines. Solutes of medium polarity include ethers, ketones, and aldehydes. So depending upon the type of solute you have to choose your stationary. Some common liquid stationary phases for GLC. You have polydimethyl siloxane. You see the temperature. This is what is important. Temperature, maximum temperature, which can be used with this stationary phase is 350 degrees centigrade. Beyond this temperature, if you operate with this stationary phase, there are high chances of losing this stationary phase. And this stationary phase is used for these type of applications. General purpose, non-polar phase, hydrocarbons, polynuclear aromatics, steroids, and for polychloro biphenyl. 5% phenyl polydimethyl siloxane is the second type of stationary phase. These are trade names, the second column. And this also has a maximum temperature of 350 degrees centigrade, used for fatty acids, methyl esters, alkaloids, drugs, halogenated compounds. Similarly, you have these other types, 50% phenyl polydimethyl siloxane, much lower maximum temperature of 250 degrees centigrade, can be used for separation of drugs, steroids, pesticides, and glyphosate. 50% trifluoropropyl polydimethyl siloxane, maximum temperature is 200, should not exceed this, and it is used for separation of chlorinated aromatics, nitro aromatics, alkyl substituted benzene. Your polyethylene glycol, PEG, common trade name. Also, you know, Carbovax 20M. Maximum temperature in degrees centigrade is 250. Free acids, alcohols, ethers, essential oils, and glycols are the type of substances which should be separated. And lastly, we have 50% cyanopropyl polydimethyl siloxane, which has a maximum temperature of 240 degrees centigrade, and it is useful for separation of poly, unsaturated fatty acids, protein acids, free acids. So these are the some examples of commonly used liquid stationary phases in GS. There are now we come to the column support. There are two main types of support used in GC. The packed column, you have two columns. So you have packed column which has large sample capacity and generally used for preparative work, and capillary or open tubular columns, which could be again of two types, wall coated and porous layer open, that is port coated open tubular column. It gives you a higher efficiency, smaller sample size, and this is used for analytical applications because the amount of sample that can be loaded is very small. It's only used for analytical purposes, whereas a packed column can be used for preparation. Recommended stationary phases for various sample types. So if your sample is a gas, what type of stationary phase can you use? You can use alumina, silica gel, zeolites, porous polymers. This is, of course, gas solid chromatography or GSC. If your compound to be separated are non-polar liquids, you can use methyl siloxane. If you want to separate the PCBs or petrochemical samples, then type of stationary phase would be phenyl methyl siloxane, polysiloxane carburetes. If you have herbicides, pesticides, pharmaceuticals, this is where our interest lies. Then you can have phenyl poly, phenylene siloxane, sugars separated with cyanopropyl, phenyl methylsiloxane, free fatty acids and alcohols with PEG, alcohol amines with phenyl methylsiloxane. Greater than 50% phenyl must be present. All these are gas liquid chromatography gas. You can remember one or two of these, particularly try to remember the pharmaceuticals, sugars, alcohol, amines, and gases are, of course, easy for you to remember. So choose what is easy for you to remember and remember certain examples. Absorption on column packing and capillary walls. So, how is the stationary phase coated onto column packing, or that is the solid support, or how is it put onto the capillary wall? Silanol groups have strong affinity for polar organic molecules. Now, silica has on its surface SiOH groups, and these groups can be have a very strong affinity towards polar organic molecules, and those can easily attach to this. In case of chemically bonded support materials can be deactivated by silanization with dimethylchlorosilane. This is the silanol group that is present on silica, SiOH group. When it is reacted with dimethylchlorosilane, then you will see a reaction like this. The H is replaced and just gets attached here, giving off HCl. So now this is the surface. Earlier it was OH as the surface, polar group and polar attachment. Now this is your surface group. This can further be reacted with any suitable reagent, like in this case, methanol is being used. So what happens is the Cl gets replaced by OCH3. So like this, you can be reacting with various other liquids in order to change the polarity of the terminal group, where the attachment is going to take place. So as you make it more and more non-polar, you can have non-polar liquids getting attached or covalently bonding to this silica surface. So to summarize the stationary phase, they should have low volatility, high thermal stability, chemical inertness, and suitable solvent characteristics, giving rise to K dash and that is capacity factor and separation factors of acceptable rate. Again, some more examples of stationary phase we have with the ranges given. So 60 to 360, 60 to 340, 20 to 280. So of course, 100% dimethyl polysiloxane gives you a very high temperature to which you can go. But as you are making it, this is the least polar or the most non-polar, and you're making this a non-polar phase or you make it an intermediately polar phase. By mixing it, in this case, you mix it with 5% diphenol. So when you do this, you can see the temperature range is also changing. Okay, this is 5% diphenol mixed with 95% dimethylsiloxane. The same 100% was giving this. When you are mixing the two, then you are getting a different temperature range. And if you mix it with 14% cyanopropyl phenyl, you get an intermediately polar phase. This is cyanopropyl phenyl mixed with the same dimethyl polysiloxane 86%. You get a totally different range. See the range here? The range you can use this with is from 20 to 280 degrees centigrade. You cannot exceed 280 degrees centigrade. So it varies with what you mix. You can have more than one liquid mixed together and then use as a stationary phase mode. Now we have been talking about coating liquid stationary phase on support. So when you are coating, naturally Film thickness. What is the thickness of the coating is important. How much you can coat and what is the ideal one. So commercial columns are available having stationary cases that vary in thickness from zero point 0.1 to 5 micrometer. The thickness is very small because you see the unit, it's microns. So zero point 0.1 to 5 microns. Film thickness primarily affects the retentive character and the capacity of a column. Now, if the thickness is more, thick films are used with highly volatile. Yeah, before I go here, if the thickness is more, the retention is longer. Okay, because more amount is retained and it takes longer time for it to go out of the thick film. The smaller the thickness, the movement in and out of the film is much faster. So retention time will also be shorter. Thick films are used with highly volatile analytes because such films retain solute for a longer time, thus providing a greater time for separation to take place. It's the same thing what I told you because thicker films retain solutes for longer time, so it gives you greater time for separation to take place. If greater time is available, then better would be the separation. Thin films are useful for separating species of low volatility in a reasonable length of time because low volatile substances will not easily pass into the gaseous mobile phase. As such, they are retained more. So for such types of substances, thin films will give you a comparable separation as thick films for other types of substances. But if highly volatile substances, you will have to go for thicker films so that sufficient time is available for distribution equilibrium to be achieved. Films are useful for separating species of low volatility in a reasonable length of time. If for such substances, if you use thick films, then it will take a very long time for separation. For most applications with 0.26 or 0.32 millimeter columns, a film thickness of 0.26 micrometer is recommended. With megabore columns, that is bigger width columns, bigger diameter columns, 1 to 1.5 micrometer films are often. So our next topic is the gas chromatograph detectors. Detector is another important component that is present in any instrument because this is the component that actually senses what is present in your sample. So how does it function? It monitors the carrier gas as it emerges from the coil. You can see that the detector is placed at the exit end of the column. So the samples are passing through the column, separations are taking place, and one by one the various components are reaching the detector. The detector senses them and gives rise to some response in the detector. So the different types of GC detectors that you have in your syllabus, and these are the commonly used ones, include thermal conductivity detector, in short called TCD. It has one more name. It is called cathodometer. Cathodometer. Second one is electron capture detector, ECD, flame ionization detector, FID, and nitrogen phosphorus detector, NPC. This is also called thermionic detector, TIJ. So these short forms are standard short forms, and you may be asked questions like describe the working of a TCD. So you should know the short form as well as its expanded form. All these detection systems we will be seeing, but before we go into the individual detectors, we will see the characteristics of an ideal detector. Now, when I'm going through this, most of the characteristics, except this one, say they apply to detectors even in HPLC. So we would have gone through all these even in HPLC. So the ideal detector for gas chromatography has the following characteristics. It should have adequate sensitivity. Now, most of the detectors, what I just named in the previous slide, they all show a sensitivity of roughly around 10 raised to minus 8 gram solute uh, to about 10 raised to minus 15 grams. So that low quantity of solute can be easily detected by all these four detectors that I mentioned. Some of them are still very highly, because 10 raised to minus 15 refers to femtograms. So that's a very small quantity. So the sensitivity of these detectors are very high. The detector must also exhibit good stability and reproducibility. The response that it gives should be stable and it should also be reproducible. Stable in the sense, it should give a response that remains constant. It does not keep varying. And reproducibility refers to the precision of the analysis. That means you inject the same sample again and again, you get the same response from the detector. Thirdly, a linear response to solutes that extends over several orders of magnitude. This means that it should give a response that changes linearly with the concentration. So, say 1 nanogram sample gives a response of 1, then a 10 nanogram sample should give a response of 10. They should be a linear response. And this should be applicable over a wide concentration. Fourthly, a temperature range from room temperature to at least 400 degrees centigrade. So the detector should be capable of operating till at least 400 degrees centigrade. It should exhibit a short response time that is independent of flow rate. So, what about the flow rate of the carrier gas? The response time should be short. So, when you're changing the flow rate, if you have a faster flow rate, the response time should be the same. If you have slower flow rate, it's the same. High reliability and ease of use. The detector should be able to be used easily, so how it operates, and also the response that it gives must be very reliable. That means the response should be proportional to the amount of the component that is getting. There should not be any addition in the response or reduction in the response due to some feature of the detector. So the next desirable characteristic is similarity in response towards all solutes or a highly selective response towards one or more classes of solutes. This we will see because some detectors are general purpose detectors which respond to many kinds of solutes, and some are selective detectors which respond to one or more classes of solutes only. And lastly, you have the detector should be non-destructive of sample. After the sample passes through the detector, if it is still retained in its original form, then it can be used for any further study. But if it is destroyed, then it has to be discarded. If there is destroyed means if there is any change in the sample, then. So this is also a desirable feature of a detector. So I think the next slide goes to the detectors. So we will see that in the next class.